Good morning everybody. So, welcome to this class where we are still continuing about the electron transfer processes, and basically we are looking for the different types of electrode processes. So, all these different techniques starting from your potentiometry to ultimately what we are discussing right now, the cyclic voltammetry. So, the voltammetric techniques are basically very important to understand the corresponding electrode processes, and these electrode processes are based on where we have the working or indicated electrode. So, we want to study whatever thing is happening at that particular working electrode, and is very important, that is why. So, basically what we are looking for, the electrode, not only electrode, but it is the electrode and the analyte solution interface. So, how that particular interface is important and how these are important in terms of the electron transfer reactions. So, what we see, we just want to plot two things, that is we call as the current potential plot. So, we have the current in one axis and potential on the other, and the typical development what we achieved so far is due to not only the modification of these different electrode types, but also the advent of new generation of computers and the related electronics, which are very important to improve these particular types of electrode processes, and we can have different variations. But the most basic one what we are looking for is the potential measurement. So, what the potential of the working or the indicator electrode. So, what we basically measure is your potential of this working or the indicator electrode is controlled with respect to what? With respect to the corresponding reference electrode. So, this reference electrode, we have certain condition what we imposed, as that this reference electrode will not pass any current. So, will not pass any current, that is very important. So, in that way we basically measure that thing, and the electronics part for that, basically what is that particular part which is responsible for measuring your potential, is therefore that we can have a static potential and the different potential values we basically get. So, what we get is that particular types of potentials were there. So, is by potentiostat. So, the electronic part of that is that arrangement for a potentiostat you should have, and that potentiostat will be responsible for measuring that potential with respect to the reference electrode. And the second component now we want to measure is your current. So, the current of the electrochemical cell how we get that particular current, because we are not allowing the current to pass through the reference electrode. So, whatever current we are allowing to pass is through the corresponding auxiliary electrode. So, we have the same working electrode. So, this was your WE, the working electrode. So, here also you will have the working electrode. So, the current which we will be going to measure for this particular type of plot is passed or passes between what? Between the working electrode, because we will have the definitely the current, and auxiliary electrode. or counter electrode or counter electrode. So, if we consider it as AE is the auxiliary electrode. So, there something else will be there. So, one particular part will be responsible for measuring your potential and the other part of the electronics will be responsible for measuring your current, which will be our galvanostat. So, these two things always we should keep in our mind, that we are without knowing the very detail of the electronics arrangement and all this, but the name of these things, the basic components what we can have, we have the potentiostat and the galvanostat for all the different types of electrochemical measurements and the electrochemical workstations what we can have, and we get the corresponding current potential plot and we can analyze for these things. So, the first thing what we are getting is your cyclic voltammetry. So, cyclic voltammetric arrangements can also be used, because once we have seen that it can go for 1 electron oxidation, that means minus electron, or it can go for plus 1 electron reduction process. So, these two processes we can monitor very nicely, but if the situation is little bit complicated, how we can handle that particular thing also we can see. So, it also uses to investigate. So, used to investigate what? That means more complicated reactions or the corresponding follow up reactions. So, if we have not a single step, so whatever electron transfer for oxidation or reduction we are getting oxidation or reduction, and those we can consider at what? Those we can consider as the single step electrode processes. So, those are single step electrode processes. So, if we can have some multi-step electrode process or processes. So, multi-step electrode processes we can consider, that means one electron followed by another electron transfer, all these things can happen, and sometimes not only that, always there will be a chance, we all know that if the corresponding oxidized pieces or the corresponding reduced pieces are not very much stable in the solution, they can perform some further reactions to undergo. So, these multi-step electrode processes or the electron transfer reactions, because electrode processes are nothing but multi-step electron transfer reactions. So, those are your electron transfer reactions. So, those multi-step electron transfer reactions can be coupled with some homogeneous reactions, can therefore be coupled, that means it is coupled with some homogeneous reactions. That means, if we can follow that there is some electron transfer reaction, that means electron transfer, one electron reduction is the step is oxidation, and whatever species is produced over there, it will have some preference for some reaction. If there is a mixture of isomers, and we will see now that how we can detect within a solution the two isomers also. So, that can be considered as the follow up reaction, the homogeneous reaction what is following electron transfer is isomerization reaction, and that we can also follow very nicely. And in fact, whatever cyclic voltammogram you get from say a potential, starting potential, and then you have the corresponding switching potential, and you get like this, is a forward scan and the backward scan. But all the different types of plots, basically what I have drawn here and what I showed earlier from the textbooks also, that they are having the different line shapes, and we all know that a corresponding type of plot, suppose the upper part of this plot we can fit it. So, theoretically the fitting procedure we can have for a corresponding Gaussian analysis type or the Lorentzian analysis, that means the shape is either Gaussian shape or the Lorentzian shape for its line shape. So, the line shape analysis is the most important and the most crucial step to understand this type of electron transfer reaction. So, what we can do, these line shapes what we achieve experimentally can be simulated. So, those can be simulated, and now commercially available simulation packages are also available. So, we can have the commercially available simulation packages which we can use it for that. So, this simulated spectrum what we get, that means the theoretically predicted spectrum where the exact line shapes are matching with that experimentally obtained. So, we get the different parameters, because basically we can say here we can extract out the different parameters like the potential what we can have, the current what we can have, the delta EP what we can have, and how their dependence on one particular important thing is the corresponding scan rate, small v basically. So, is millivolt per second scan speed. So, how it is related to all these things. So, we can through that means through simulation we can therefore be able to establish a number of mechanisms, because all these electron transfer mechanisms are so important from materials, from our life processes and everywhere. So, what we can do that for using this software packages, the whole voltammetric plot or whole voltammetric curve can be fitted. So, whole voltammetric curve can be fitted and optimized. That means, is not that you can exactly reproduce the experimental curve, but as much as possible you can match the corresponding experimental curve, and from that what we can do, we just basically extract the data, extract the parameters, and therefore, we basically obtained the best possible, which otherwise is not possible from the typical experimental plot. So, best possible kinetic from the rate and all these, and thermodynamic, because in doing so what we can get, that we can have to fit some equation, and that is why we can have some simple equations like starting from the Nast equation, then Ilkovic equations, and all these different equations can be established. And once we establish these in terms of either the current or the potential, we can extract out so many other parameters like the diffusion coefficient what we have discussed earlier. So, is the best possible way to extract out your kinetic and thermodynamic parameters. So, these things are very important, and if we have therefore the very overlapping plots, so they are not very much separated, such as when we start from here, you can get one thing, and before going for its resolution, that means going to the baseline once again, a second voltammogram starts appearing, and you can get the first one as well as we can get the second one. So, this we get for a typical scan, and if we have isomers in solution, then only we get this sort of plot, and we expect this sort of plot, particularly when we talk in terms of the corresponding metal ion complexes. We can have these two isomers. We all know that facial and the meridional isomers. So, you see that with respect to the corresponding potentials for say oxidation, that means if we try to measure the corresponding oxidation potential. So, the first isomer is oxidizing here. So, if you have the mere isomer over here is fast oxidizing, that means in a medium these are all octahedral complexes, because we get these two isomers in some NiL3 type of complexes, where L is your bidentate ligand, and you have definitely of two different donor atoms like nitrogen and oxygen. So, NO donor type of ligand, when it binds to the phase, one phase where one phase basically occupying all nitrogen and another phase is also occupying all oxygen. So, we get the corresponding facial isomer, and the other one is also the meridional is spanning same donor groups. So, if you get the first oxidation potential for that isomer is fair, the meridional, then the second one will be the facial isomer. Then if we go for your reverse scan, the facial isomer what has been oxidized over here will now be reduced over here, and next is your meridional isomer. So, if we can able to do these things, and also the corresponding temperature effect for these voltammetric processes, and how we can vary it, how we can go for this, we change the corresponding proportion of these two isomers will also change, and that can also be shown for their relative responses in the cyclic voltammogram, where we measure the corresponding current against the corresponding potential E. So, if we find that what should be your corresponding differences, because this difference, this separation, this delta E value for these two isomers are sometimes so overlapping that we cannot get this sort of thing very nicely. So, what we expect, we get something where we can go for the derivative one or the differential one. So, what we can go for differential current, we can follow. So, differential current measurements we can achieve it, and that is why a new technique basically, because the differential current measurements will basically give rise to a technique like your, this was your CV, and that's next one is your DPV, differential pulse voltammetry. So, you have a differential current, and the P stands for your pulse technique. Pulse technique. So, the very first thing what we will be getting over here is the one where we do not have this differential one. So, will be your normal one. So, your normal pulse voltammetry will be NPV. So, before going to your DPV, we should know a little bit about the normal pulse voltammetry. So, what we get? We get the step and pulse technique. So, it is not a step as well as the pulse one. So, once you have the pulse one, so step and pulse technique is useful. So, again with the development of your electronics part and the available computers, and there are little bit small computations also are very much needed. So, the development from that part, the electronics part and the computer part is very much important to get this step and pulse technique. And what you have? We have the succession of potential steps, succession of potential steps we use of different height of varying heights. So, that basically give you the shape of these different steps, and next we get the corresponding pulse. So, it is not a continuous one, it is a pulsed one. So, what we get there is a staircase waveform. So, as we discussed earlier that the different waveforms are available, and these different waveforms, how the triangular waveform is used for your cyclic voltammetric measurements. So, now we are looking for something where we can consider it as a staircase waveform. So, how the nature of this waveform can be useful for getting the corresponding E value and the corresponding I, sometimes we also write it in the small I. So, the current. So, how we generate those potential pulses? So, short potential pulses are generated and which are given to the electrodes. So, in normal pulse voltammetry in NPV, what we do? We basically use there the short potential pulses. So, they are very short potential pulses are used of increasing height. So, what we see there, because we should know about the nature of these. So, is the break. So, it is going and is breaking at some point. So, its height is increasing, but this particular time axis is not changing. So, that means the time width for these different pulses are same, only the strength of these pulses are changing. So, it is coming back again to the baseline. So, when it is coming back to the baseline and we get something, and this basically the separation between the first one to the second one we get, and the time frame from here to up to this point is your tau prime, and the time from here to this point is your tau, because this tau and tau prime values have some significance for these. And when we get this, so this change, the pulse changes because the delta E values are there. So, these are the corresponding potential values. So, is the corresponding potential axis and this is your time axis, and when we figure out for these for the normal pulse voltammetry is that your tau values will be in the range of seconds, it will be 2 to 4 seconds range, where the tau prime is in the range of 5 to 100 milliseconds. So, the separation. So, these are the corresponding variations and the continuous variations what we can impose for this sort of measurement. So, you see everything is computer controlled or rather electronics controlled for these sort of measurements. So, when we get these as increasing height of delta E values of these pulses, so what we have again the potential is coming back. So, you get or you give the short pulses, these increasing height pulses are giving on a constant base potential, because it is coming back to the original potential value. So, that is why we get original plot. So, what sort of our current potential plot would be then? So, you should know that what should be the normal pulse voltammetry and how the corresponding plot will look like. So, it will be like this. So, it is a typical staircase type of plot like our all cases we find for potentiometric measurements also. So, this can also be done in using the dropping mercury electrode. What we know from the very beginning that the historically is also important to get that dropping marker electrode for the development of polarography. So, this is your I axis, small I or capital I, whatever it is. So, it is the current axis, and this is your potential axis is your E. So, this potential axis you can have and is moving in this way. So, when we use the dropping marker electrode, so the drop lifetime is there. If we consider the drop lifetime is same to that of your this corresponding generation of these pulses, it will be very easy to monitor these things in terms of that. So, when you finish it, when you come back to this particular position is your end of pulse. So, when you finish that, that means end of pulse will be equal to your drop falling of the drop or drop fall of DME. So, you get a fresh or new dropping marker electrode, new drop of mercury you are getting, and that new drop of mercury is utilized for your second pulse, and the third drop is for the third pulse. So, in this way it will be very useful for this normal pulse voltammetric measurement. But nowadays with the development of other parts also, we can go for a differential one, which is your DPV. So, how we know that? So, because it is a very useful technique. Why it is useful, that we will see. Just now what we have seen, that is if you have a very overlapping potential. So, cyclic voltammetry cannot give the good resolution for that. So, you have now for the DPV we have the superimposed pulses, So, how one of them is your staircase one, and another one is the square steps. So, if two of them basically match together, we get the corresponding pulses again in the basis of tau and tau prime. So, what we get now is very important and interesting also. You get this and you come back and you get this, and this go up and this. So, this is the waveform. So, we should know the shape and nature of the waveform, particularly for your differential pulse voltammetric measurements. So, these differential pulse voltammetric measurements are useful in that way that you have not that earlier we have seen in normal pulse voltammetry your base potential was not changing. So, it is coming back to the base potential. Now, your base potential is your staircase. So, this base potential is changing in a staircase manner, because the staircase we have imposed on something where this is are of the same height. So, this particular one from here, so what are those your tau and tau prime values? So, this is your one will be your tau and another will be your tau prime values for this. So, we get these superimposed pulses. So, we get basically the corresponding current responses, because this is the potential versus time axis. So, whatever current responses we get over there, so is then plotted. So, we get the difference between two currents. So, we basically get two different currents and you have these pulses again. So, tau is basically going from 0.5 to 5 seconds, it can range, it can have the corresponding range from 0.5 to 5 seconds, and your tau minus tau prime would be in the range of 5 to 50 milliseconds. So, these time frames are very important, that how short or long durations you are utilizing for generating those pulses. So, you get the difference between these two currents. So, this difference in current that can be either you consider as delta I or del I basically, and we plot these basically. So, this when we plot, so is plotted against the staircase potential. So, is plotted therefore against the staircase potential, because this potential is changing. This is your time. So, staircase potential. So, we get this delta I versus your staircase potential. So, delta I versus staircase potential will give rise to all these things, and how we will analyze it and all these things we can discuss in our next class. But what we plot, if it is your delta I and is the plotting against the potential. So, we get from the very baseline, it will basically change like this, and a very sharp plot we get corresponding to the potential. Only one potential is fine for this oxidation or reduction, we do not get the reverse one. So, this is your corresponding plot for your DPV. So, in the next class we will see how we can utilize this and how we can find out this when we have the corresponding overlapping plots. Okay.